All right. Unfortunately, we missed that part of the portion of the class, but all right. So now we're going to go to the next types of basically positional encoding, and it's called rotary position embedding, RoPE. And this basically, this idea, this technique was introduced as in a paper for row former, it's called like instead of transformer, it's called row former. And then also recently in DeepSeek paper that also you see that basically this is the new technique that's being used. This new type of positional encoding, it's introduced basically some new characteristics to your positional encoding that especially those are kind of like gives you relative distance between words instead of fixed distance. And also it's kind of rotation invariant. What's a relative versus fixed distance? If you think about the word dog here, maybe at position 1 versus dog versus cat at position 10, this is at position 10, this is at position 1. It's just at 1 and 10. That's basically how the sinusoidal or the original transformer works. And the idea of RoPE is that if you're on the word dog and you look at the relative distance, like this distance is 9. So basically it tells you that, hey, this word is 9 words after you. This word is 2 words after you. So the model gets some relative information of how much distance between words are, right? And this tends to basically overcome this challenge that of a longer sequences that we saw here. That so this RoPE technique basically it has some benefits. It helps with preserving the preservation of the length, related positional information, and it's going to be a rotation invariance. Now, the main idea behind RoPE was that they use really kind of like a similar function. So the formula is kind of like here the same. Now, the main basically thing that they introduced was that if you're looking at a word like a dog, and the word dog has an embedding which is d by 1, the idea here was that instead of just add a frequency value to every index or every embedding value, what we will do is that we break this d by 1 matrix into basically into, and it's going to be right now crazy, but it's going to be d by d distance matrix or rotation matrix, which what you basically do is that imagine you have this position 0, 1, 2, 3, all the way through d, right? So the idea here is that create pairs of positions across your embedding. So position 0 and 1, they go together. Position 2, 3 go together, 4, 5, and so on. So if you have D, you end up with D by 2 position, right? D by 2 combination. And you convert this D by 2 combination to a matrix like this. We will see how. But the idea here is that if you look at I think we have one. First, let's talk about this theta. So we can basically apply some sort of like a rotation to this to every pair. So like I don't know if you're aware of the rotation matrix, but that's a definition of a rotation matrix. So in a 2D form, so R theta is a rotation matrix that it has cosine theta minus sine theta, and cosine theta, right? So that's a rotation matrix. So if you pick one of this, like this one, for example, that combination, and plot it. So let's say So that has only two values. That means two dimension, correct? So let's call this embedding 1 and embedding 2. Across an embedding vector, you pick the first two elements, first two number. And well, you can basically plot it, the RoPE, that's the vector. So for location, like a E0, and then for location E1, or maybe let's just call them embedding 1, embedding 0. That's this exact value. That's the vector, right? So what basically we are saying here is that we want to rotate this vector. In order to rotate it, you multiply it by this rotation matrix. So if you multiply that vector directly by this rotation matrix, it just rotates it. So now this becomes move E1 here, E0, so and then E1 here. That's a rotation of the same thing. You just change the location of this one goes here and the other one goes there. And that could happen simply by multiplying it by this 2D rotation matrix. Okay. Now, so that comes the first step. For every pair, basically, what they did, every pair being multiplied by that matrix, you get a new representation, like a rotated representation. Okay. So now, we have a good image actually, so I don't need to draw it. So think about here, what you see here, you have all these words, enhanced transformer with rotary position. These are each word. And every word basically has this long vector as embedding representation. You break these vectors into pairs of embedding values. So first one, as you see, is like this one is one pair, this is one pair, and so on. So if you have D vectors, you get D by 2, D over 2, basically, sorry. So, and then here we basically put a theta for first one, theta for second one, and so on. And you can basically, as you see, as we saw over there, you can basically present this in the following format. Then, instead of using this, we want to use this rotated version of it. Okay. Now, bear with me. We're going to understand why we actually do something like that, but what's the benefit of this? So, if you look across this D by 1, and you convert this to, technically D by 1 becomes D over 2 elements, right? Every D over 2 elements will be multiplied by this matrix, correct? So we can create a R theta or theta matrix here. So here, basically, as you see, R theta for position M. M is the position of the word in the sentence, and D is the length of the embedding. So this becomes R M theta and D. So why we get D by 2, D by D, why is squared? Because for every pair, you multiply it by 2 by 2 matrix. So D by 2 times 2 by 2, again, goes back to the same dimension, becomes D by D this time, right? So this becomes the D by 2, the D by 2, all the way 2 by 2, 2 by 2, 2 by 2. So total, this becomes a D by D matrix. So this is, if you want to look at it from a matrix perspective, instead of multiplying every pair by this, you can multiply the whole matrix, the whole vector, by this matrix. And this gives you the same impact, basically, the same rotation in a matrix. So now, one of the things that we talked about this was that, hey, this will introduce, it's kind of like a relative distance, right? And we want to understand that, okay, where this relative distance basically come into play. Like all we did, we multiplied, basically what happens is that you bring your data multiplied by this matrix, you get your data back and you do the same attention, right? You do still same attention. So where is this notion of relative distance, right? And that comes around the dimension, this equation that we have. So all we want to see about is that you have this large matrix for every word, and you multiply that large matrix because it's fixed, this large matrix, right? It's like a same thing repeating d by d. So multiply that by the Q matrix, you know, for basically one word, right? And you also multiply the same thing by K matrix, because that's what we do: multiply by K, multiply by Q, right? So you multiply that matrix by queries and by keys. Now let's see the impact of that multiplication. So if you do this transpose that, so the transpose swaps the order, so you get Q transpose R K, right? So now if you think about this, let's go back one page. If you think about R theta, just this the version of 2, if you transpose of that, what do you get? If you apply transpose of this, what do you get? Minus. The negative of itself, because the diagonal are the same, the off diagonal just negative goes down. So that's exactly equal to negative of, right? So if you bring that knowledge, we know that R theta transpose equal R theta negative of I, technically. Okay, so now use that for this dot product that we are doing. So R theta negative times R theta J, right? And we don't want to go in depth. We actually have those in the slides. But if you prove that, do this multiplication, expand it, that is, this transpose is equal R theta J minus I. That simplification of this multiplication becomes R theta J minus I, right? And the full proof is in the new notebook, but it's just, you can expand it based on the cosine sign, and then that's what you are getting. So the multiplication of this two term gives you R theta J minus I. What was J, what was I? J is the position of the key. I is the position of query. What does this become? Relative distance. So by simply using this equation rotation, you automatically, the model learns the relative distance between query and keys. It's kind of like we pick the formula somehow that explicitly get this later. Does that make sense? So again, the derivation why this reached to this is you have the full derivation in your notebook. But if you carry on basically this terms, that becomes this. And J minus R is the distance between two indices.
How we got the R of theta for J minus I, but like what is that? I didn't understand how exactly that provides the notion of position.
So let's go back one. So here, when you're looking at what we are doing attention score on, what do you see on the attention score? Between query I, key J. What is I? Index of the query. What is J? Index of the key, basically. Okay. So J minus K becomes the location of key minus location of query, which is the relative distance between the two words, right? So the benefit of this technique is that the relative distance always remain the same. Doesn't matter even if you rotate this matrix, J and I, they always have the same relative distance from each other. Okay. But if you think about in the other version that we have, it's not the case. You know, you're adding some positional values, so then it's like you don't keep this. Basically, you don't have this relative distance information. You just add some value, add some position to the encoding. So now,
so that's hard theta. Like, do we hard code it or do we learn it through training?
It's hard coded, so there's no learning on it. So
the theta value that we choose.
What is the theta value that we choose? So that was the next slide. So think about the what we are basically saying that theta, you do sine and cosine, so it should be a degree, right? So you have I think the main basic idea here is that if you, like in 3D, you can find this better online. If you in 3D you look at this as a globe, and you can break this down into something like this, like a 45 degrees maybe, for example. Position 0 starts here, then position 1, 2, 3, 4, 5, 6, 7, again 8, 9, repeats, right? And the angle basically is kind of like becomes fixed depending on where you are falling. So how do you calculate that theta? So if you have two vectors and you want to calculate the angle between them, so if I have this vector and this vector, and you want to find the theta between them, basically we can use the cosine, right? So first find these two values, and then do a dot product among those. You do cosine inverse. Here we do clamping to ensure that the range is always between some values, for example, and then you convert that to a theta on a basically circular form. So that's how you can calculate that theta for words, basically, between two vectors. Now, let's do one example. So we have a sentence: the dog slept, and you have 3 words, and here we assume that every word has an embedding of size 4. So for word 1, for word 2, and word 3, you have a 3 by 4 embedding matrix. So the first thing here is that I assume the dog is the query. So D is the key, and slept is also the key, right? So here in a 2D, I created the arrows. So in order to show this in 2D, what it means, I basically ignored the third and fourth dimension. I use this to plot the points, but I use the same formula that you saw to calculate the theta among those. So it says the angle of D with respect to dog is 53 degree. Dog with respect to dog is 0, and slept with respect to dog is 61. That's the angle of these vectors. Now, our goal is that we want to introduce RoPE and then do attention basically here. So we have 3 matrices similar to for any attention: WQ, WK, and WV. Those are like your weight matrices. So first thing we need to do is remember what's going on in this equation. So in these equations, if we go, actually let's write this. So we have cosine of theta minus sine of theta, sine of theta, cosine of theta, correct? That's repeats basically. So what we want to do, we want to calculate for every pair. So remember, it should be pairwise. How many, the embedding, what was the dimension of embedding? Every word, 4 values. How many pair you get? 2. So that's why here you have pair 0 and 1, means the first 2 elements, and pair 2 and 3, the second 2 elements. Okay, so you start with the first pair of this embedding. So if your embedding has only 4 dimension, it's 4 by 1. So you get 1, 2. So you start for the 0 and 1, and basically, how many words do we have? We have 3 words, right? So every word basically has, so dog has this, D has this, and slept has this. Same thing, 0, 1, 0, 1. Okay? 1 value, 2 value, 1 value, 2 value, 1 value, 2 value. You have 3 of those. So basically, you're going to calculate 3 values, cosine and sine. So cosine becomes for the first value, for example, sine becomes for the second value. And how do you calculate that? So you just need to use the equation that you have up, find the thetas. I is the location, P is the position in the sentence, right? So if you think about, for the word, so the sentence start with the dog slept. So D is position 0, first position. So in this here, P, which is the position, will be 0 for D. Then you have I. and you have D. What is D? D is 4 because we have embedding of length 4. Right? What is I? I is the location. Which location we are referring to? Location 0, for example. So that becomes 0 divided by that. So that's the value. Then you go to, so you calculate that for word D, first position. You calculate that for word dog, first position. And you calculate that for word slept, first position. You get 3 values. So you get 3 values. Then you go to second position of this embedding, which is this one. This one, this 1, 1. We are still on the 0, 1 pair. Then you pass that to the same equation. This time you pass it to a sign after that. So you find the theta and you pass it to a sign. You get 3 values. So we have, for pair 0 and 1, you learn 2 things, sine and cosines. Okay. Then you do the same thing for 2 and 3. So now this time you go to these values, this one, this one, this one, and this one. And you have 3 words, so you basically get 2 matrices of size 3. One for index number, like a position 0, index 3, position 1, index 3, position 3, 2, index 3, position 0, index 4, position 1, index 4, position 2, index 4. Position means the word. Index means in the dimension which index you are at.
I have one question. We came up with this whole method because of 2 advantages. We said we wanted to be rotation and vary, and we said we wanted to be relative, like from 1. I have an argument. I think it's, first of all, I think our previous method was relative because the relativity comes from P. Like that P changes in sine and cosine, here P changes too, in my opinion. And the second was that one issue that we had with sine and cosine, after depth 60, it became just 0, 0, 1, 0, 1, 0, 1. So it doesn't carry any location meaning. But here the same thing happens. Because I is in denominator. After some I, that theta goes towards 0. Like for example, after I, let's say 50, then we don't have that depth again.
That's really a good observation. So what do you think is the main difference between this and that? What did we do in the first general positional encoding at transformer? You find then positional encoding, and then you did what? You did add it. What do you do here? Multiply it. Well, it's not additive anymore. The impact is really different if you add something 0, 1 versus you multiply here, right? So that's one of the things here is that you don't add anymore. You just multiply this whatever representation, encoding representation by the embedding. Scale the embedding by that. Versus adding it is just, if you think about at the end, you just add 0, 1, 0, 1, as the impact is kind of like some of them get 1, some of them.
After some depths, it's just you are doing the same thing for every depth. Like after, like it's just 0, 1, 0, 1. It doesn't become like some positive, some negative, that cosine sign.
Mm-hmm.
But I cannot get, like you say, multiplying, like.
Let's do a multiplication here. We'll see it. Okay. So now let's put that together for the first basically pair that we found, location 0 and 1. So if you go back here, what did we find? For the first position, we have these values, this values, this value, this value, this values, right? Okay, so bring that here and put those together. So cosine of theta repeats, you know, if you look at the first element, what's the value? 0.54. That's cosine, right? Cosine repeats here and cosine repeats here. So if you go to matrix, cosine is on diagonal. And off diagonal becomes sine and in the negative of the sign. So you create these 3 matrices for the 3 words, the first pair, right? Then you do the same thing for 3 matrices for second pair, basically. Okay. Now, instead of in previous embedding, you just add those matrices. What we do, we multiply those matrices. Okay. So now let's look at the let's go to the words before.
Makes a difference, yeah.
Let's look at the value. So if you just do additive, if the one that almost 1 and 0, there is no change here, right? But here technically you scale the data by doing this multiplication. So you basically get a better representation of the space, and especially for longer sequence. And also by nature here, basically explicitly you get the relative distance between pairs, which in a general transformers, you're not aware of that, right? The model is not directly aware of that. So you basically enforce that on the model. So this again turned out to be much better than the general basically positional encoding that was in the transformer paper. And the latest version of the model, RoFormers, or like the latest papers, they're all doing RoPE instead of that, because we found out that the main problem with transformer was that as the sequence becomes longer, embedding becomes larger, that becomes problematic. That enforcing of the position by that sinusoidal and cosinoidal is not enough. It's not relevant to the information. Beyond certain dimension, is kind of like it loses its meaning. So this is more relevant or state of art right now. Now, that's overall. Again, there are other techniques that they are doing for positional encoding. You will find online more techniques, but I think this is right now the RoPE is the main one.
So do we add start and end keys here like we did earlier? Just like, when we're talking about a sentence, you add special characters like start and end, right? We do that.
You mean in the RoPE?
Yeah.
So in RoPE, you have a query. So you have a query basically, and you have all these keys. So you still need to attend to every key. So you need to understand the relative distance of the word to every key, like positional. So you need to still do the RoPE for every key values.
Right.
Because you still, if you think about it, you just do a multiplication to every key. So you do that, correct? So it's like it's not just for the current query and previous word. It's like whatever you need to attend to, all the keys.
And is there a way to handle the odd number of, we just did the example, so it's fine.
Yeah. So from the perspective of odd and even, that only cares about the depth, not the number of words.
Right.
And normally you need to keep the depth to be an even number. So it's like it's 128, 256, and so on. You don't select an odd one.
So in previous slide, we studied like vectors, angle between two vectors, but then we came up with a hard-coded formula to calculate based on.
So the angle. So we okay. So let's talk about something. So the technique that being used is rotation matrix. In order to rotate a matrix, actually, let me go back to this image. In order to rotate a matrix from here to here, that rotation comes from m times theta. That's how you get the rotation. So you need that theta, because you're using this rotation matrix, and your rotation matrix need that theta, that angle, in order for you to rotate. So we find that angle, and we use it with the rotation matrix to rotate the basically vector.
So like we are not concerned about like angle between vectors.
It remains the same technically. So because it's invariant. That was what we were saying. So it remains the same. The relative distance remains the same. The angle remains the same. You are not shifting them technically. But you basically, you are shifting them. You are not changing them.
I didn't completely follow along how the new embedding was got. How we got the new embedding? Like we got the cos, we got the rotational matrix, which was like a combination of three matrices. The multiplication that happens after that with the embeddings. Like,
So you have these three matrices.
yeah, no, not these.
You got these ones, right?
I got that.
Okay.
I got the rotation.
You got this,
Yeah.
and you got this.
Yeah.
Okay, so you multiply this. So if you think about, let's look at one example. Let's pick this one. So look at the first word in the sentence. So we have 4 dimension, like for vector of 4. So it's going to be 4. We're going to get something 4 by 4. How? Pick the first part. What's the first part? It's a matrix of 0, 5, 4, 0, and minus 8, 4, 1, 0, 8, 4, 1, 0, 5, 4, 0. Okay, then it's 0, 0 here, 0, 0. Then you have another matrix, is diagonal, and this matrix comes from the second one, which is 0.999 minus 0, 1, 0, 1, 0, 0, 1, and 0.999. You build this matrix, right? 4 by 4. Now you multiply this matrix by key vector for the location m equal to 1, which was the word d. So you have this 4 by 1 vector. If you multiply it by 4 by 4, you get another 4 by 5, 4 by 1, right? 4 by 1 times 4 by 4, you get another 4 by 1. So that becomes the first row in the new matrix.
Yeah.
And for the second row, which is the second word or the query word, you have original embedding, and you have this matrix, not the exact, this matrix from this, the second element of this, you do the multiplication, you get the second row. And for the third one, which is a key also, you do the same thing. So you get a new embedding, and you use that new embedding for the general attention that we were doing. Make sense? All right, so now, so that again, that's just a general idea of the positional encoding and basically how we can enforce the model to learn about positions. Now, the next thing here is that, okay, what if we, like this question, if we stack bunch of attention on top of each other, like if we, like we are doing like a self-attention, we repeat it, like build like a layers of attention, just like that. Can this learn something like multi-layers LSTM when you stack LSTM or iron on top of each other, right? So think about like this, you have words that being introduced as different timestamp. Okay, so this words goes to this attention or like a self-attention mechanism, and for every word, so at every timestamp, every word is the key, the query, and every other word becomes the key. Then you do it. Inside this, there is some self-attention happens, and which is the self-attention, if we want to plot it technically, is if the query comes through and you have these keys, you do, or you have this lowercase also, then you do query transpose key, and then you do a softmax basically on that, and you get an A1, for example, if this is query number 1, key number 1, you get an attention. Then if you repeat this, let's say T times, because you have T words, so we have T words, what do we get? We get attention, a score all the way to, there's no softmax here, it's just dot product, T of this, and you do a softmax here, you get the attentions, right? That happens for one query at a time. So for the first query, you do all of this, you get these attentions, then you multiply this attention by vector V, the values for all of those, because it's not like a scores. So you do a dot product is a summation, and what you get basically is some output, which is one vector, okay? This is a vector of attentions, times these are the V's, so you get one vector, okay? So this becomes output of this, O1. Then you go to the second part of second timestamp. Now this word becomes query, the previous word is a key, and every other word is also a key. You do the same loop, and then you find O2. And you go all the way until here you get OT. So every word will attend itself and every other word, and you get some output basically. Now, what if we stack this on top of each other? What if we put another self-attention here? What if we do that? So now the key query and value to this new layer are O's, not the data anymore. So this, basically this O1 through OT will be query, key, and value for the next layer. And you repeat the same thing. And then you can stack more, stack more. And the question here is that if we just do something like this, we'll, it's like, does the model learn something useful? Because if you think about it, that is simply like a nested or a recursive function. If you can literally write it in terms of one large matrix multiplication. Because it's just nested loop, times, right? You can multiply the V's all by together. Like you can multiply the alphas like that all together and basically calculate the end. The challenge here is that if you keep repeating this, your model doesn't learn any nonlinearity. Everything is linear. It's like a linear multiplication, right? And that's why if you think about in transformers, we have after every self-attention, we have a layers that we have to feed-forward network, right? So you introduce that feed-forward networks because we want to introduce some nonlinearity. So here we're basically using a ReLU. So you get the output, you pass that output to a feed-forward network that has a weight and a bias. So it's simply multiplying. So basically, what basically we are saying here is that instead of doing this first, you have this feed-forward model that gets this one, O1 times W, some W for feed-forward, plus a bias term, and you pass that to some nonlinearity, for example, a ReLU. And then that becomes the output. That goes to the next layer. Because if you just stack them on top of each other, everything is kind of linear projection. So you want to enforce nonlinearity. So it's really important in transformer architect that we have this feed forwards because that's where we introduce those nonlinearities. Does that make sense? So
We use one feed forward for each word.
no, so you just one feed forward, like one model. Yeah, here just the representation, it looks like that. So, and then if depending on the downstream task that you have, could be a softmax at the end you're adding or so on. Now, so that's all around the encoding part. This all you saw so far is around the encoding, the positional embedding that we introduced, everything we were talking about encoding. And as you can see also, the encoding is pretty expensive. In encoding part of the transformer, every word, in order to find the output for one word, you attend to every other word. So if you have n words, you have a complexity of O and 2. Because you end up this with large matrix. So it's pretty expensive. That's why if you think about from the complexity perspective, the encoder is more expensive than the decoder, the generative one. Right? Because, just the amount of operation that we go through to create those encoding representations. So now we go to the next one, which is now let's go toward the generative part, the decoder section. Now, the first thing in the decoder is the concept of feature masking. Okay, why? Because if you want to build a model that generates, the model should not see the feature states. So the model always should have only knowledge about past and the current timestamp, right? Nothing about the current timestamp that you're predicting, nothing about the features. So in generative, like in the decoder part, the GPT part, the first thing that we will see is going to be different. Instead of self-attention, it's called masked self-attention, right? It's not anymore. It's the same idea, but it's like a masked version of the same. Okay, so how does that work? Like for example, these are two ways of doing it. One way is that when you do masking, you look at the index. If the index is less than the token, the key index is less than the query index, you keep the attention. Otherwise, you set the attention to 0. That means I know this is a next word, so I'm not going to attend to it. I set the attention to 0. So that's one way. The other technique is that which is more common is you build a matrix like this. So if you have n words, and in encoder we know we end up with an attention of n by n, right? Or it's a matrix of basically n by n in the encoder, and you have all these attention weights where they sum to 1. In the decoder format, what you do, you create this basically matrix that the upper basically matrix upper part is like all 0. Oh, sorry, minus because we want to do the second approach, minus infinite, minus infinite, minus infinite, and you basically only have these values. Why minus infinite? Because if it's softmax of a large negative value, probably goes to 0. So you enforce the raw scores to be really large. So when you do softmax over this, these are get a probability of attending of 0. So that's another way basically that of doing it. But that's the whole idea of mask self-attention. You still do self-attention, you just, before calculating that either, if you first calculated the attention weights, then you use the first approach. You look at if the index is after, I change it to 0. That's one way. The second way is that before calculating the softmax, you just force the dot product, that the score that you have for future words, to be minus infinite. So if you do a softmax, the attention for this one goes to 0. And so like this is like, there are I think more ways that you can do that, but these are like 2 ways of doing that. Any question on that? All right, so now, anyway, the overall component, if you want to build like a minimal self-attention, is that you need a self-attention block, a code for that. You need a positional encoding. You need to introduce some nonlinearity, which is that feed forward, and you need to do feature masking. So technically, you need 4 components. One component that does the self-attention, because it repeats in both places, encoder, decoder. One component that introduced the positional encoding. Positional encoding is also in the GPT part. So in both cases, you have embedding plus position, then goes to the model. The positional encoding is part of both. Then you create the feed forward for the nonlinearity, include the nonlinearity, and then you just need a feature masking. Okay, this is like a general. This is like a minimal approach. We don't have a cross attention yet. Okay, this is like a without connection between these 2, like a separate from each other. So, yes.
This is all decoding, right? The masked one.
Yes, so this is the decoding. What I was trying to say is you can use the same thing in the encoder also. Just remove the feature masking. That's for the encoder, the first 3.
So why would you need attention when encoding?
In the encoding?
Yeah.
So that, remember, so when you encode, and think about what are you trying to do? You already have words. Words that already have an embedding representation. Correct? Embedding representation is always fixed. It's fixed for every word. You want to learn the contextual representation of the sentence of word with respect to other words. That's why we do self-attention.
Right.
So encoders does the self-attention and creates the contextual representation for the entire sentence and per word, basically.
And then in the decoder, we start calculating attention scores again, and then.
If you are doing encoder, decoder together, then the decoder gets that information from encoder to do the translation, for example.
So the contextual information, that is also attention here.
The contextual information was generated using attention.
And then the decoding prediction is also generated using attention scores and softmax.
So I think we will have a better graph for that come out. But yes, so think about something like this. So you have an set of word or sentence basically, and you want to encode it.
Yeah.
Okay. So you pass it to encoder, and encoder, it does everything from positional encoding, self-attention, feed-forward neural network, adding some and basically doing some dropout, right? And we are just doing one layer. We haven't talked about multi-head and stuff like that. And gives you an output. Now, how many output it gives you? It gives you technically one output per token, because it's an encoding the token, right? What we do, depending on the downstream task that you have, and we will see, if you are trying to just simply do a classification, you don't need a decoder. There is a token here we call CLS, right? So CLS is think about what you want to do. You want to introduce a token before every other token in your sentence. You put a CLS token fixed at the beginning. It's called CLS, just you can call it whatever you want, but just for classification. So this token, because it's at first, is the first token in your sentence, so it can attend to everything. It's not in the center, it's not at the end. So you put a token at the first. This token, overall, as you go through this embedding, first time itself is a query, so it attends to everything. Then as you go through this, it basically influences everything. So it's kind of learn knowledge. So this CLS token, if you want to do classification only, you only pick this, the last layer of the encoder. The last output of the encoder is that. So you pick that, and that is considered as a contextual representation of the whole sentence. You use that for classification, I don't know, for search across documents to see if two documents are similar and stuff like that. Now, if you want to do other tasks, like I'm encoding, so I can convert it to a different language now. Then I'm not going to, or I'm doing name entity recognition, for example, or like tasks that I need individual values. Then you don't use this anymore. You use individual output. It's about the downstream task, how you want to use the encoder overall. But encoder gives you different outputs, and depending on what you want to use, you select that output.
But attention is used in both encoder and
Yeah, encoder here is self-attention. It's like, and we're going to see it's not just one time, it's technically a series of self-attention. We will get there. Right now, so far, we have talked about one self-attention, one layer, right? We're going to expand that to multi-head self-attention, multi-layers concept, and then we will see how this one. Yes.
So this is just a shot in the dark, I can say. So logically, can I conclude that because let's say I have n tokens I have inputted there, and I got n tokens out of it. Let's say only one encoder block we have right now.
Mm-hmm.
So if I pick the let's leave out the CLS token aside and pick out the first token I have next to the CLS. So can I say that represents the first input I have given? Can I make that assumption or hypothesis?
The first token representation, you think, for example, if I have an X1 here.
Yes, that indirectly it will represent the X1. Can I logically say that?
Sorry, you're saying that this O1 indirectly represent the X1?
The encoder block, yes. Because it is encoding the X1.
So yes, so think about what we are trying to do in attention. You still try to encode the same word,
Yes.
but with respect to every other word.
Every other, yes.
So the value, so if you think about from the perspective of embedding, right? Embeddings, if you look at, I'm not really good at plotting embeddings, but if you think about like you have, I don't know, like a 3D embedding, and this is a word, for example, king, right? And let's say, for example, this is a word, war, right? And this is a word for a country, like, I don't know, France. And I don't know, this is a word for like a killed. Like the king was killed at war in France, something like that, right? And you have all this embedding representation across different words. Now, what we try to do here is that let's say the king is the first word, the query. And we know king has a fixed vector. But what we try to understand here is that if I'm trying to encode this representation of this king, which one of these words will help me to understand the king better, right? Because all you have about king is a fixed representation,
At the start.
not based on the context. In this context, this king was killed, right? If you don't learn based on the context, king is the same king. Whereas if you have another sentence that he is the best king, people love him. If you don't do contextual understanding, king is king across both of these documents. So what we do is, if you think about it, these are vector of same dimension, right? If you do this plus that plus that plus that gives you another vector. And that vector technically has some meaning, right? That's the whole idea of embedding learning. Well, we say, instead of just summing this, let's sum those based on how much, which one is more similar, which one you should attend to more. And that's where the attention comes.
Yeah.
So you do a dot product after you do the positional encoding. You do a dot product, dot product, dot product, convert the dot product to a softmax, right? So the softmax gives you the probability. Like the softmax tells you that this king, and I don't know, let's say killed, because it was more emphasized, attend more to the king, like, and then, I don't know, France, and then war. So when you do it, what happens here is that the final representation of king becomes the king itself, like the vector, times whatever is the attention score for it, plus attention score times France, plus attention score of war times war, attention score of the killed times killed. All those becomes a scaled version of these vectors. You sum all those vectors. The new vector that you get for this king carries all this information. Basically, in the contextual understand, it has a contextual understanding that this is a king of France that was killed in a certain war. So that's the idea. By doing this, you teach the you're presenting your words, encoding your words somehow that they are not only carrying their own information, they carry information from other words also, whatever was relevant. So as you sequence through this, every word has a right to attend every other word. Maybe there's a certain, maybe, I don't know, maybe kill will only attend to war and find war more important than the other ones. So it's the model basically learned those, how to attend those.
So now comes to my main question.
Yeah.
So I don't know whether I'm judging forward or not. So basically the training, the encoder part at least we have done right now. How are we judging it and back propagating it? How?
We haven't gone to the training part, which is the after this we go to
I thought I
the
did.
idea of training, but the main idea I just quickly tells you is that it's similar neural network. You just do a sentence and you produce the same word.
Oh.
So encoder is just that. When you build embedding matrix, you know how you do it? It's like basically you build a neural network like an encoder. You get words encoded, regenerate the words. If you keep doing that, and you are able to pick a word from one hot representation, for example, condense it to a vector of size 128 and reproduce the same, and you repeat it across all words that you have, at the end, for every word, you have that contextual 128 representation. That becomes the embedding of words, correct? You do the same idea, but it's kind of the same idea. So you pass words in, right? In BERT, basically, what they have done, or if overall in the encoders, we're going to have talk about this, but in the main paper of the BERT, if you have tokens, you want to produce the same token, predict the same token back. But what they did, 80% of the times, they mask a token. You don't know the token, the model need to predict the token. Right? 80% of the words was masked as you go through the training. I think it's randomly 20% of the words were just they were replaced with a wrong word. They were not masked. You just replace it with some wrong word. I don't know if it's 20% or something. We will see the next part. But replace with the wrong word, and you want the model to predict the correct word. And I think it's like a 10% of the words you keep fixed. You don't change it. So you run this large amount of data. Similarly, these are large models. These models that they run for days that goes all over the Wikipedia's data as like a book data or whatever is like the data that they use, and becomes next. Basically, you get the data, you want to predict the same data. Right? It's not a next token prediction, it's current token prediction, basically. So if you do that a lot, your model basically learns to how to embed, like it learns because you mask words and you replace words with the wrong words. In order for the model to understand, well, the word war should be here. It attends to everything else to understand what's the context of this sentence. The king was killed where? Well, war comes to the point. And the meaning of the war comes from that attention and at the end times that we vector. Right? And that's just simple forward backward propagation.
So realistically, encoder and decoder always comes together in the training process.
No.
Okay.
Separate. This is separate. There's no decoder here.
So without the decoder, how is it getting back all the words it has?
Softmax. Just put a softmax here and the last layer of this model.
Got it.
At every timestamp, if you have, I don't know, like a D words, N words, you have a softmax of over N. You give N probability, you pick argmax. So you predict it, then we go to the next one. So in generative, there's a difference. The output of the next one goes the input to the next one and so on. In encoder, it's not like that. You just make one prediction, you have a label for it, and later you use that label for back propagation. All right? Yes.
So the way you explain, but like we mask few words and then we try to
More than a few words, 80% of the words we mask.
we try to learn the embedding, right? Unless it becomes highly accurate, right? But in the transformer part, in the encoder part, you mentioned there is.
So that's the same thing. BERT is the encoder part.
Yeah. So there was a feed-forward layer after attention, right? And you said that it add non-linearities.
Mhm.
There we are doing something like this where we learn things or like.
Yeah, so let me go to Bert later. So he asked me a question, how we will learn. We haven't even gone to, we need to go first multi-health, then we go to multi-layers, and then we go to Bert to see that how they stack this on top of each other. Technically, Bert, I think, has about, like a 12 layers. Each layer has like a 10 heads or like those random numbers I'm throwing. But it's a really large model. So we will see those stacks. Yes, it has a stack of attention, nonlinearity, dropout, attention, nonlinearity, dropout, and so on and so on. It's not like a stack model. It's just we're just so far learning one layer. All right, let me go through this and we can take a break. So actually, let's take a break here now. We stop on multi-head attention. Let's take a short break and then we continue from there. Continue. All right, so we're going to start with something called multi-head attention. Now, the idea was that up to this point, when we built a layer of attention, like if this is one layer of attention, for example, if this is an attention, like a self-attention layer, if we just call this layer one, up to this point, this layer one only had one self-attention in it. Okay, basically. And now the idea here is that, well, what if instead of doing one self-attention, we do P self-attention in every layer? That's the idea of multi-head, basically, self-attention. So instead of just having one self-attention, you do a series of self-attention. Now, why do we want to do that? Well, the thing is that when you do one self-attention, think about the concept of it, like in a layman term, think about convolution. When you do one filter versus you do 10 filters in one layer, you learn more by using more filters, right? Here is the same idea. When you use one head, you only use basically one concept, every head focuses on one topic. When you add more heads, every head basically will focus on learning something different about the data. Same idea of that, what we do convolution multi-filters basically. So that's the idea here. So we basically do multi-head self-attention. And all the papers, like the transformers, all of these models, they are multi-head, and you don't see one head basically self-attention. So we're going to now talk about that more in details, but the idea will be that for every head, you perform same attention and same softmax for every head. Exact same thing, repeat the same thing. But every head will get a different weights. So if you have like a head one, you have W query one, and then you have W K1 and WV1, those weights. Then you go to head two, you get W query two, W K2, and WV2, and so on. So they have a different weight, similar to kernels, but they have different weights, so to learn different things, basically. Okay, now, so this becomes the representation of the multi-head. So you have, in here we have this input, thinking machines. So there are two words, and every word has four embedding, four dimension on the embedding. And we want to do multi-head, and we're here, multi-head means three head, basically. So you have head one, head two, head three. So for every head you, head one, head two, head three. For every head you have three matrices with the weights for query, key, and basically values. And then you multiply this by that, you get three matrices, query, key, values. You do dot product between query and key, you do a softmax multiplied by V, that's the output. That's what we saw in the self-attention. So you end up with 1, 2, for example, 3 here, outputs. Now, if you do more than 3, like a multi-head, so you get basically lots of output. Every head has a different, basically, output. Okay, so that's the idea of multi-head attention. But then that brings up this question, well, I'm getting multiple outputs for every location. Every head for the same location gives me an output. And I need a mechanism to be able to handle that, right? So the idea for that mechanism is that if you have this, for example, here we have 7 outputs, stack them on top of each other, multiply them, linear multiplication by another matrix W, here over there shows with WO, the long matrix, and that will ensure to convert it back to the dimension that you want. So there were 2 words, 2 by 4 again, you get as an output. So you have, think about it, you have multiple heads. Every head give you an output. So the output of this head is, let's say, because you have 2 words, is 2 by 3. The output of the next head is again, let's say 2 by 3, or 2 by 3, and so on. At the end, what you would do is that you stack this on top of each other, right? Depending on how many heads you have. Then you want to be sure that you can multiply this stacked matrices by a weight matrix that you are learning, somehow that it produces the output that you would have get if you just do one head attention. So if the output of single head attention would have been a 2 by 4, you pick this matrix W somehow that after concatenating this multiplied by this gives you the same dimension.
So essentially what we're doing is linear combinations of the multiple heads.
Yeah.
So are we trying to learn which head is more important in a certain context?
We will basically learn. So so every head will learn something new. It's not like a more important individually, but based on the context, definitely you will get that. So we have a playground that we will go over. So every head gives you a different attention, and you can basically see that in this head, the model attended to this part of the sentence. In this head, it attended to this part. So every head, again, really similar to convolution we do, that every kernel maybe learns something different about the image. Here, idea is the same. Every head will learn something different about the sentence. And per word also, every word might attend. So for example, word dog might attend to word sit in a head 1, but in a head 2 might attend to a word cat. Every head basically focuses on something different about the data basically. Now, so here basically we concatenate those and we multiply by a matrix so to convert it to a projection. Yes.
If I have this right, at every timestamp, one word is given to multiple heads to self-retention.
Yeah.
And then whatever is concatenated and
Multiply by a matrix and you get the output.
okay, got it.
Wow, like all the attentions from every head is meaningful, like they're meaningful for sure, because the model is not confused or anything, because.
No, because let's say that's a good question. What if the Z's that we get, they are really strong, right? You have that weight matrix that you iterate with, like a back propagation, you update that WO. So you let the model to learn, well, you had 7 output and they're all of them almost important. But, you need to decide which one is more important, or maybe you want to give, if they're all important, you give a higher weight here. So this becomes summation across, right? So that whatever output you get is going to be really large. That means you attended to, like, every head's output was really important. And the model has freedom of updating that weights to adjust it for the better, basically, prediction. Now, so this is an example of the output of the multi-head.
Yes, previous W not like, is it hard coded or like during training?
You learn. In attention to transformers, those W's you always learn. That's the whole idea. So here, what you're saying here is that, so you have 8, here how many you have? I have 12 heads. So every head, as you can see, we will go later to this playground to see it. But what you will see here is that in layer 1, the blue, like this is the attentions. Those are like the attention weights. And as you go through layers, you will see attentions becomes different. So for example, in this layer, the word is attending the next one always. Or it doesn't attend to anything else. Like in this one, like I don't know, like CLS attends to the separator, for example. That doesn't attend to anything else. So every head, it will learn something different. So it's like they have some, we need to interpret it to understand what they actually try to learn. But that will be the idea. Now, if you have all of this basically, and you multiply them by the weight, by values, and you convert it to a matrix, and you put them on top of each other, right? Concat them on top of each other, you get this long representation, and you multiply that long representation by a matrix to give you an output. That becomes same idea. You repeat it n times and concatenate them, and just multiply it by a matrix weight, like matrix W. Now, this becomes kind of like an across all. So if you look at for this across all head, for example, like these are the values that you got per head, basically value. So that's the idea. Now let's see. Soon we will have this playground that we can test out these attentions. But now the question here is that, well, this becomes super complex probably. Right? We just, instead of doing one self-attention, now we are doing like a P self-attention, right? The interesting part is that you actually don't add any complexity. Same complexity, multi-head versus one head. How?
Because we concatenating.
No.
You tie the weights.
What was that?
You tie the weights.
No.
You're breaking the input space into multiple space, subspace, basically.
So so this is a general self-attention. You bring data and you multiply it by, so data has d dimension, right? And then you multiply it by basically this, you get this Q, you do this you get the key and multiply. This one block. In multi-head attention, you break this down into the number, whatever number of head you have. So instead of doing in one head, doing everything across all your data, you break the dimensions that you have. So into, like, instead of, for example, one head one head, if you have one head technically, so think about, I have this data and I want to multiply this data by a matrix WQ. And if my data is n by d, let's say this WQ, for example, was d by p. Okay. The p is the new dimension that you will go. So in just one single attention, that's what you do. In multi-attention, what we are basically saying is that I don't need to use all d. If I want to have k head, divide d by k, see how many head it will give you. Okay. Then instead of having d by k, you have d over k. So this becomes an small. Now you have series of this. You have basically k smaller matrices. So you break your matrix into k smaller dimensions, matrices. Right? And then you do this multiplication. So you do a smaller, basically, attentions technically. Instead of doing one large attention, do a smaller. What was the idea? The idea here is that if you think about these vectors like that, we have this vector representation. Every dimension of this embedding learns something about, has a meaning, has an angle. For example, if you think about again, king and queen. Let's say this is king, this is queen, and this is man, this is woman, right? That means this direction means like royalty. This direction means, or the other way around, means gender. Every direction in the embedding has a meaning. So instead of processing all of this together, what if we process them in the smaller sections? Right? That's why every head will get a different, basically, part of the data to work on, right? The different smaller chunks, weights, basically, and learns a different thing. So heads, basically, they are learning different things. Then you bring all those learnings, concatenate them together, and combine them to some other learning, like a linear projection. The benefit of that is, if we just do one single head, you basically tackle the data in one go, one wheel. Have one weights, one WQ, one WK, one WV, and I'm just going to do one linear, like a one transformation. In the other way, you're like, data has different meanings, and I'm going to tackle it different times. And I bring those different learnings, and then combine those learnings into one total learning. Multi-head attention by default is like a much better than single-head attention. Like your model learns way better, right? Single attention is like so easily to go, like model doesn't learn anything or just overfitting. Multi-head, same complexity. You don't even add any additional complexity. It's same complexity. You run it on parallel also, probably much faster technically, right? So same thing, same dimension, same complexity, much better results.
Do we also learn this number k, right? How many heads we will have?
That's a hyperparameter. You decide. You don't learn it. You choose it. This is like hyperparameter.
Is it the concept behind mixture of experts, right? So you basically divide data into sections.
So let's put something on that. Yes, there is a concept on selecting it. You don't pick it randomly. Why? Because these models are not like you train one K and if it wasn't good, you pick another K, because you have one shot to learn. Sometimes you only have one chance to train one model. So yes, there's a concept behind of selecting K, but it's a hyperparameter technique. It's not something that the model learns, basically.
Yeah, so in here, I understand the advantages, but because we are splitting the dimensionality D from D to D by K, are we not losing the positional context information?
Why you like positional context?
Let's say we have a vector of D, and
Position of the word is fixed. You're dividing the embedding.
yeah, embedding. We are cutting it. Basically, what I'm trying to imagine is like, let's say that the word the or a king has a position embedding of 128. Let's say what length of 128. We are splitting it to, let's say, 64 and 64. Yeah. So because we are splitting it, are we not losing any information? Like because we are splitting it and we are sending this half into one part of the calculation, this part into a different part of the calculation. There is no interactions between these two calculations so that they don't share any information. Are we not losing any information moving forward? That's my imagination, I guess.
So you're sharing the information at the end. You do a 1 head, 2 head, 3 head, and then you concat those information and do a linear transformation on it. So you still get the same information back, but you learn more richer, more focused information from every head. And you have another weight which is responsible for combining this. However, it makes better sense.
Because in my imagination, at least, I am unable to imagine more than 4 dimensions. But let's say I have XYZ coordinate. I am removing Z coordinate. That's what we are doing, right? We are removing the Z coordinate and we are sending it away to a different level of calculation. And we are using XY coordinate and using a different level of calculation. Are we not using losing that particular, what do you call, depth of information from XYZ, having an XYZ coordinate to an XY coordinate? That's how I am imagining it.
No, so again, let's go back to the embedding. When you're looking at these words, when we say that this direction has learned like a gender, or this direction has learned the royalty, across that D, that direction means one value. If you have a word, the word has this 0.2, 0.999, and so on, embedding. This, only that means gender.
Yeah.
Not all of it. This direction
Represents that that direction it is.
So every direction in this, and normally the earlier direction, they have more fluctuation, more learning. And as you go toward the end of the embeddings, that's kind of like plateaus, that those, depending on the types of model also was used. But breaking it down, it's, if you think about from learning perspective, passing a really long sequence to the model and says that do linear multiplication and everything and calculate the meaning is more complex than breaking it down into smaller chunks and says that you learn individual things and then I combine your learnings.
Yeah.
Right. So that,
If this is the one, that makes sense. Yes.
Any default recommendation for going with number of heads?
I don't have a default recommend. I mean, they are all sort of basically every paper has a different thing. And if there is a paper that they publish, like for example, certain of the models that they don't tell you even what's the architect and stuff like that. And in my domain, I don't go more than like, I don't know, 3 heads, something like that. In the lab also, I create those videos that I put for the labs. Also over there, I tried with like a 3, 4, and for the task that I was doing beyond 4, I didn't get any improvement. But again, that's not the case for large models. For a smaller task, maybe yes, you don't need to go too many layers, too many heads. You need to add layers, which will be the next topic that we're going to talk. This is just head, so 1 layer, multiple head. Now we want to talk about what if we go to multiple layers, right? So we add more, basically, the dimension to this. So, see, there's no video. Oh, there's some image here to go over. Anyway, so now if we want to basically put this together in context of transformer, this is how it looks like. Basically, input comes through. This, assuming that you did some positional encoding, goes to multi-head self-attention. Okay, that is like a multi-head, not just one. Then there is a residual connection. Remember the idea of residual connection, ResNet. So there's a residual connection. Then that in paper you will see it says add and norm. This is add. That's the add part, adding part. And then this is the layer normalization, which we saw also as part in the convolution. Then you again do here, you do feed forward basically for nonlinearity. You have another residual connection. You do another layer normalization, and you do output. This is the output of one transformer layer, just one layer. Now, if you stack series of this layer on top of each other, which that's what happens in reality for the large models, then you need to, the output of one layer becomes the input to the next layer and continues. So layer 1 gets this as a key query value. Layer 2 gets this as a key query value. And layer 3 gets the output of the layer 2 as a key query values and so on. That becomes multi-layer concept. Now, and this is just that's the for add and this is for layer normalization, which we saw in the convolutional chapter. Okay, so let's see. Where did I? It's some sort of like images here, like a GIF that to run over, but maybe it's later. Okay, so again, that's the residual connection that helps us with the gradient flow and also identity mapping and just the keeping track of information in longer sequences. And yeah, so now let's go deeper to understand that how this works. For the add and basically normal add and norm that you see. So word comes thinking, it has this vector representation. Machine is the second word, has a vector representation. Let's say thinking is the query, and this is key and query itself, right? Here, this sign is positional encoding. Whatever positional encoding you do it here. Okay, either you do RoPE, you multiply it, or you do normal positional encoding, you add it. Then you get a new representation. New representation goes to self-attention. Self-attention gives you like a latent representation. Bring the latent representation, add the data back to it, and do a layer normalization over that. The output of that goes to a feed forward, and then you do add and normalize, and the output goes to the next layer. That's the general idea of this, just with one head. This is not a multi-head. Okay? So it's just a general idea of the self-attention. So now, what we saw previously, and I think we talked about in the previous class, was that overall idea of attention was to be a dot product. But we found out, just if you just do a dot product, the problem is that it scales with the value of the square root of t. So if you have two vectors, you do dot product, the dot product keeps getting larger and larger if the vector is larger and larger, right? So that becomes a challenge because everything, all of a sudden, the values are really large. So it scales with the square root of d. So in order to get rid of like a d scale, that in the basic paper, they divide the dot product by a square root of d. It's kind of like a normalizing the dot product, basically. That's the whole idea. It doesn't change anything. It just normalizes the value before the softmax. So, all right, now we want to talk about transformer architecture. Now, transformer architect, basically there are three types: encoder, decoder, encoder, decoder, right? So when you hear the term transformers, it's either one of these three. If it's encoder, it's like BERT. If it's decoder, it's like a GPT. Encoder, decoder, like T5 or span correction types of models. T5 is the one by Google. It's kind of like for more like it's sequence to sequence versions. So now encoder, this is from the original paper. So the encoder basically looks like this. Input becomes embedding. You add encoding, and the encoding gives you three arrows: query, key values. So that's the three arrows: query, key values. But before that, also the encoding goes for the later. So it's like basically a skip connection or residual. Yeah. So this three goes to multi-head attention. You bring it up to add and normalization, goes to feed forward, add and normalization, linear softmax. This is encoded, and the softmax was what we were talking about. If you are predicting the same token, so encoder was trained basically like that. So it's like you predict tokens, same tokens at the top, using a softmax. So let's see. There's no image here.
Dimension of the output of the softmax is the same
Dimension of the number of vocabularies that you have. If you have D words in your P words in your vocabulary, at every softmax you predict P probabilities basically, and you do argmax among those.
So so we come back to the earlier question. So the first position corresponds to the first word of the input, right? The max sort of at least.
Yeah. The first position is for the first
and the second one, the second one.
So So transformer encoder, so actually there's no image here. So this is just encoders applications, and which we talked about. If you're trying to encode documents, you try to learn contextual representation of documents. In general, the BERT, we will talk about it. The goal for BERT was multiple things. One was that they wanted to predict the next sentence. That means it's called, there's something called entailment. What is the chance that this sentence comes after the next previous sentence? Entailment, like how this entails with that one. So that was one of the goals that BERT has. The other one was what next, basically the token prediction, mask token prediction. Now, when you go to the decoder, now this is the general decoder architect. You have almost same thing. Insert the mask, the self-attention multi-head attention becomes masked multi-head attention. You don't see the future. You should basically kind of block the future either by setting the dot product to minus infinite or setting the attention to 0 for any future word, basically. But it's the same concept. However, when we go to transformer, the architect has a slight change because now you want, this is encoder decoder. Now you want the encoder to share information with the decoder. Because of that, there is a new layer in the decoder, and that's called cross attention. Okay, so what will happen? Encoder is the same encoder, encodes everything, and encoder will produce. Remember here we have the encoder actually. Let me just keep that. So the encoder produces this basically O outputs, like an OT outputs. Every output itself is a vector, like a contextual representation of the word. Then you have a decoder. So decoder starts with one sentence, like a start sentence, a start token. And it basically wants to predict what's the next token. It goes through basically multi-head attention, like positional encoding, multi-head attention, like a mask multi-head attention, because it cannot see anything in the future at the moment. Add, normalization, everything that we saw up to this yellow part, which is add and norm, okay? Now, at this point, we have a vector representation for this token. But we want to use this to predict the next token. However, we want to do that using this. That comes the cross attention. So this value here is a query. The output of the encoders are key and values. So you do cross attention, same multi-head attention concept, same attention concept, but cross attention. So this will attend every keys or every output from here, does a same dot product, calculates self-attention, calculates the attention score using softmax, multiply the softmax by the same like a vectors, which is the like a V representation of those, and gets the output basically. So this basically comes attends here, and this goes to another layer, which is an add and normalization, feed forward, softmax, produce a word. The word that was produced will come back, and then as an input goes here. I goes here, mask self-attention. This time has two things to attend to, itself and this one, the previous one. Goes through the same thing, gets this Q. This Q attends to every word again from there and continues. Produce the next one. That's the idea of basically when you see this translation or generative model, basically this with the cross attention, that's basically what happens. You have a token at the time, you make a prediction, like a mask at self-attention, feed forward, add normalization, you get the vector. That vector is your query. You do a cross attention with that query and output of your encoders, all of the outputs for that sequence. And all outputs for that sequence start at the same time, key and query and value. You do cross attention, calculate the softmax, like the attention scores, multiply the attention scores by V, sum those, you get one value. That's the cross attention value. You pass that to add and normalization, feed forward add and normalization, softmax, predict the token, and repeat the process. Is that clear?
That value and key that comes from the encoder part.
Yeah.
That's for the previous sequence sentence.
Same, no, so when you do encoder decoder, normally the task is translation, summarization, and stuff like that. You don't regenerate the same thing, right? If you want to regenerate the same sentence, you just need an encoder, right? You use encoder decoder. I have a language. I want to go from English to French. For every word of French, I attend to every English word that I saw in the document.
What about sentence generation kind of thing in the same language? Then we don't.
That's just a GPT model.
Oh, we don't need any.
You don't need encoder. Well, you basically so that comes around here, depending on what you see as a GPT, but this is technically a GPT. There's no encoder here. You do one token at the time, you make a prediction, and based on the probability, you update the weights and continue. You let this to train a lot to the point that these weights that this GPT has, it's really good at next token prediction. So you need to remember that there's like encoder alone is just for embedding of the data. Here. Decoder alone is just for generation. Encoder, decoder is for like sentence translation, text summarization. Like this one gets a long text, and this one is responsible to make it shorter, basically like maybe 20 words, right? So those type of things, depending on what you're using, this different architecture. Yeah.
Since the purpose of is like translation, stuff like that, then the output of the encoder should have some relation to the input of the decoder, right?
Yeah, so you train them together. So when you do, so you convert this to some representation. That representation goes to this model. You get there, you make a probability, right? A prediction. Here you do backward. Backward goes here, and also backward goes here. So you train these two together technically, right? You could also have a pre-trained encoder and just trained decoder, depending on your application. We will talk about this later.
So the number of tokens that we can pass to like encoder or decoder, what factor determines that?
Ooh, we will get to that. We have slides on that. Just bear with me. But you can just think about it. If the encoder part is more expensive than the decoder. Encoder is always n times 2. If your sentence, the larger the sentence, the more expensive the encoder. Decoder is much cheaper. It's still, if you think about this general decoder, you still do quadratic, because despite the fact that you don't attend to the future, you still do a quadratic basically calculation. So it's done pretty expensive. That's why the longer the sequence is like it's the attention part. Now imagine you do lots of attention, multiple layers, not multiple head. Then that becomes more complexities.
So you said that in the encoder decoder transformer architecture, we train them together.
If you train them together.
If you
Google,
want to-
Google, for example, for T5, and they train them together.
So what is the point of training them together? Because encoder part.
Because you don't have a good encoder and you don't have a good decoder, you want to have a decoder encoder that is task specific. They do things together.
Okay. So parallelly, the decoder waits for the encoder's key value pairs, and they will be basically waiting for each other's to complete their
Think about
specific part. And
well, yes, so one needs to learn to do a really good job at encoding. The other one needs to learn a good job at decoding. In autoencoders, for example.
yeah,
Encoder, decoder. It's like the same idea, right? So that is that's the cross attention in details if you want to look at it. So the output of encoders, those hidden representations will come as a query and as a key and value goes to multi-attention here. And the output of the decoder comes as a query. And you do this times this to basically to get the attention output.
Is it a sequential?
Where the decoder is always sequential. So encoder need to first go over the entire sentence. Then the decoder can run.
So the query and the key and the values is a whole sentence.
You have a whole sentence goes here.
Yeah.
You get
Key and the value.
you get n output, you multiply it by 2, you get 2 of those basically. You use one of them as key, one of them as for value, for example. Then you go to the decoder, 1 token at the time you predict.
First token has code. Like the key and the value for whole sentence have been sent. So the key and the value for every token will be same or a different?
They're not the same. These are different. You mean the key and value?
Yeah.
They are the same. You have different weights, so you use them in a different basic
Key and
perspective.
value is same for every token.
In the cross attention, only in the cross attention, not here, not here, only in here. Only in this red spot, H, which comes as an input to the cross attention, are key and values. And those key and values are the same only in cross attention. Outside of the cross attention, you have different, because think about what happens, you multiply them by a W, right? Here, actually, if you think about it, when embedding comes, embedding is the same for all of them. You multiply by different Ws, you get different representation. Here, you get 2 same vectors, basically, you multiply by different Ws, you get a different representation of those, then you continue with the multi-head attention with respect to the query that comes from here. Does that answer? So just overall, the key query, like when you start, key queries and values at beginning are the same for encoder, decoder. In the cross attention, the key query comes from, key values come from encoder output, query comes from the decoder. Okay, so not find that, but anyway. So yeah, this is just the same thing that we saw before. And this is for the final layer, and you just apply a linear projection and the softmax, and they're making get those log probabilities for predicting the next token. So let's go to this. Okay. Now, what if we have multi-layers? So here what you see, you have 2 encoders, encoder 1, encoder 2. Encoder 1 does the same thing that we saw. The output of encoder 1 becomes key query value for the encoder 2. And the output of encoder 2 becomes key and value for the decoder 2. Decoder 2. Yeah, we have a decoder 2. This is decoder 1, decoder 2. So it repeats the same thing, just output of one goes to the other one and so on. So here goes to here, here also goes to here. So every decoder will attend to the encoder's output. Every decoder, when it does cross attention, will attend to the encoder's output. So if you have 10 decoders layer, you basically do 10 cross attention to the same thing. You just need to always remember this. Yes.
So when you take the output of the encoder, it's like the encoder of the final layer, right? And it's not
Final layer only. All right. Okay, so let's look at this. And this is here that we have a visualization. It's basically how it works. You get a token, you bring the token, you do decoder, decoder attends to this encoder's key and values, predicts the next token comes here, goes that. And you see the encoder is pre-populated. It's already populated, so you don't do it while generating. You do it before the generation. Okay. So this. Okay. Now, the drawbacks of these models, well, the quadratic computational complexity of these models are the drawback that we have, and so the transformer itself that has the highest complexity. You have now the new architecture on transformers, for example, lean formers, RoPE formers, all of those basically try to improve that complexity, make it more efficient. But it's kind of like it's important to remember that they're pretty expensive. And then we talked about also for positional representation, there are alternative methods that you can do, like a relative, that's what we saw, like a RoPE or rotational. They're like a syntax-based position. And I think we don't need, we will see that. I'm just going to go to this playground for now. We're going to the next document, see that. So I highly recommend you to play around, go on this playground. For this is called BirdViz. It's visualization of the bird, and bird is the encoder, remember? So now if you go, I thought this by default is running. Oh, so, I need to sign in, so. I'm not going to sign in. I leave to you that to play around with that yourself. Just go to that link, sign in, and that's the where that you see the multi-heads. So you can basically try out to see the different attention values across heads across different words. All right. It's like a public machine. I try to not log into emails. Now we're going to start with pre-training, and
I have a doubt that's bugging me, Professor, sorry.
Yeah.
So you said that encoder is kind of like very computationally expensive than decoder? Kind of, right?
not exactly, both of them are quadratic. The decoder, from the time perspective, everything is sequential, is like a slower. Encoder, the time complexity is like from time perspective, encoder is probably faster than decoder, much faster, because you do cross attention in parallel. You don't need to wait for cross attentions, right? So, but the number of
Parameters are twice the amount of the encoder.
yeah,
That's
it's
why
more than the other one. So it's kind of like but it also depends, like it depends on what's the structure you use, like how many layers, how many, basically what's the overall. It's not an apple to apple comparison, right? It's overall, what I'm saying is that the encoder has more operation to do because they need to do cross attention across everything. But it depends on how often you basically repeat that also. In decoder, you do masking, so you do less operation, but then it's sequential, so it's like there's no parallelization in it, right? Okay, so we're going to start with the concept of pre-training. I don't know why. Now the idea of pre-training is that you have like you basically train one model. We call it base model, a larger model, basically really like a strong model that normally these base models are taking much longer time and cost for building those. So you develop one of those models over a large amount of data, and that becomes your base model, and you fine tune basically that base model. That means you pick a model that someone else has trained and you try to tune that to do a specific downstream task for you. That becomes the idea of fine tuning. And what we have seen over the basically last 2 years, over 3 years, this becomes really popular, the idea of fine tuning and basically overall like a transfer learning, and these days more like a knowledge distillation around like models that becomes more popular and more affordable for smaller organizations than in compared to large organizations that they have a vast amount of data and money to train those base models, right? For example, that's what we saw, what happens with DeepSeek, that they have a really strong base model, and then they basically transfer that knowledge, like distill that knowledge into much smaller model that can do the same task, and it's much more efficient. It's kind of like there are different ways that we will see that you can transfer this knowledge. Now, previously, the easiest thing that we can remember as concept of the basically pre-training is the word embedding, right? We have been using word embedding, like if you do any NLP task these days, it's kind of like a state of art to do word embedding instead of one-hot encoding, right? And we normally try to not learn our own word embedding, and we use basically trained BERTs or mini BERT, RoBERT, and all those basic versions of the word embeddings. So that's the previous version of the pre-training. It was like having a embedding basically representation, right? Even before BERT we had different embeddings that like much smaller embedding models that you could use for token embedding. So that's like this is the token embedding, and the idea was that, well, let's go to one layer after token embedding. Let's do the sentence embedding, for example, right? And then like a BERT came to the model, or the GPT model, like train a really large model for generating text, and basically use that for some other task. Or you have a model that understands language, and then you basically bring that model and fine tune it to convert language to query, right? So all of those are possible if you have a really good base model. That's really important. So all this fine tuning and stuff like it happens if you have a good base model. Without a good base model, it's like the downstream model, or basically the fine-tuned models that you get are not going to be really good. Now, but now the idea here was that, as we talked about in the previous part of the class, well, how could we learn that reconstruction of the input? How could we basically learn this BERT? How could we learn to pass data and reconstruct the data? Now, what we want from these types of model is not to just reproduce the same word, is actually to understand the syntax, to understand the semantics, right? To understand the grammars basically of the language. That's what we mean by contextual representation. It's not just one dimension. It's like an overall, everything about that word. Now, in here, basically what you can see is that, for example, if you think about syntax and like article choice, basically say that I you leave something empty and say that fork down on the table, and the model needs to basically pick the correct basically article to fit that context, Or if you say that, for example, co-reference resolution, the woman walked across the street checking for traffic over shoulder, the model needs to understand the co-reference her shoulder, basically. So those are basically things that you expect this model to learn. Semantic category learning is like, for example, I went to ocean to see fish, turtle, seals, and the model needs to understand that dolphin or whale, they could come here because they're kind of like semantically similar. Then you can do sentiment analysis. The movie was whatever, the model understands that it's like a positive or negative based on that review. You have spatial and location understanding. Zuko left the model needs to understand that, for example, based on the syntax or the context that it was in, maybe left the kitchen, or maybe, I don't know, left the room. It's kind of like that's understanding of spatial and basically location. Then you have geographical knowledge. Notice a university location located in, you leave something empty, the model should say Boston, for example, or Boston, Massachusetts, right? Those are, and then like a sequence prediction, like you put the Fibonacci sequence and you leave something empty, the model need to be able to predict that. When we say we want a model that is able to contextually understand the data, it's all of this. If you look at it from a language perspective, it's not just to predict the correct token, to overfit to the predicting token, to memorize the data. It's to be able to understand all of this. And that's why, as part of the BERT training, we will see that not only we predict the next token, we also replace tokens with wrong tokens to see if the model is able to correct that. It's just the idea. So,
the previous slide, like in that Fibonacci sequence, that's crazy to me. Like, I mean, because these numbers, they become some vectors, but then I don't think it can pick up the next number, honestly. A large language, can it? I don't know.
Yeah.
Because I think
play around with it, go to ChatGPT and give it a try.
no, that ChatGPT, I think, can predict it because it's seen it before.
Yeah, so So, okay.
But if I give it a new pattern instead of Fibonacci, something that it's not on the internet, it's not on the web, I think it cannot
That's a
understand.
really great observation. So when we talk about pre-training, these types of model work good if they have a really good global knowledge. If you pass a data at this stage to the model without reasoning, the model jumps to the conclusion and gives you a wrong answer. That's why the new generation of the model that you're working on is like it has reasoning. And the idea is that instead of quickly give an answer, have chain of thoughts, break down the problem into subset, solve like a dynamic problem, like a suboptimal answers and reach from the suboptimal to the optimal basically answer. Right? Instead of just jumping to the conclusion. So if you give a sequence to the model instead of trying to give you a wrong answer, trying to learn what's the patterns in the sequence, that will become an idea. But if your sequence that you're providing the model comes from the general knowledge, they have seen it before, probably they have learned it, right? So, okay. Now again, the pre-training idea is that data goes through, you have some sort of model, and the decoder predicts the next token. This is a decoder version of it. So the encoder, what we talked about, you want to learn the contextual representation, and decoder also has that contextual representation, but the goal is that to predict the next token, not the current token, basically. Now, so the overall idea basically here is that, so if you think about what I want to do with pre-train, fine-tuning and stuff like that, it's basically we said pre-tune once, fine-tune multiple times. That should be like the idea. If they share with you that pre-trained good base model. Some companies, they do that. For example, Meta does share that they pre-train models because that's not their monetization strategy. It's like, so they build the model on purpose and release it, which is great for research community, right? You have a really good base model that you can work with. And other companies, of course, they hide it. But here is the idea is that, so you have this model that's pre-trained on language model, and now you want to use it for classification. So you basically pass the data to the same model, for example, and instead at the end, you maybe add an additional layer to this model that like one final fully connected layer that's just a classification binary output. And we're going to talk about that's the idea of fine tuning is like you change the model for maybe different downstream task. Okay, so now we can basically use the stochastic gradient descent to do fine tuning because if there are different fine tunings, basically schema we will see as we go down. But in a general idea, like you normally don't change the weights and parameters of the pre-trained model. What you do, for example, you add a couple of layers at the end of the large model that you have. You keep the rest of the model frozen, fixed. You add maybe 2 fully connected layer at the end, or 3, for example, just this number. And only train those 3 using forward backward. So you update enough that model. It's so quick because now you don't update any other weights. You just update the last 3 layers. You only update those 3s for your downstream task. So if you do classification, you have a classification data that you use and you do supervised fine tuning. And you just basically update those last 3 layers. So you do a really good job on that classification task. Right? And all you need to do is to do some sort of like a stochastic gradient descent or some version of this gradient descent. Now, overall, what we will see as part of here is going to be encoders is going to be like that. Encoders, decoders is going to be like this, and decoders is going to be like this. And then we're going to break this down further from the perspective of pre-training. Now, let's just start with BERT. So the idea, the overview, basically the BERT they had is developed by Google, and so included. So let's look at here. It has 30,000 tokens. That means the dimension of the vocabulary was 30,000. It has the embedding has 1,024 dimension. Embedding included 24 transformer layers, so 24 layers, each layer with 16 heads, basically. Okay, so that's just think about it. That's what I was telling you, that the size of these models are not small to learn. So much larger models. So this was, I think it's first BERT, it's called large BERT right now. Current BERTs are much smaller than this. But the way that BERT was pre-trained, it's something like this. So you have sentence, and you have this large encoder, basically model, and you basically say you leave something empty, and you model, for example, you change the word, like instead of went, you put pizza, and the model needs to predict this was went. And 2, the model predicts the same thing. It was supposed to be 2, and then E, your model doesn't predict, so it just has kind of like some stochastic nature to it. And then if this one is masked, you all of a sudden leave it empty, you don't know what's it just masked, the model needs to predict something. And you do the same thing over and over again over all your data, large percentage of the data. So the actual paper, I think they used 80% for masking, 10% for random swap, and 10% they keep unchanged, basically. So, and basically to feed that to lots of layers, lots of models, basically large models, lots of training, lots of examples, to get to the point that model does a really good job at the final task, the output task. And when you have that model has learned the contextual representation of the data, basically. That's the idea, right? Because all those maskings that you do, your model learns all those things that we talk about, like grammar, syntax, it learns about entailment, it learns about locations, because you've masked all these words, your model need to predict those. Now,
What is that segment embedding?
That's actually a good point. Sorry. So in BERT, the original BERT had 2 main outputs, basically. One was that to do the token prediction, and the other one was that sentence prediction, entailment, that if this sentence will come after this one. So if you have a long document, this document is dot separated, like a sentence separated, right? So you encode the segments, that means the sentence. So when you say segment encoding, segment embedding, basically you say that this sentence is the first sentence, the next one is the second sentence, and so on. So one of the tasks that basically BERT was trained on was that to predict if this sentence should come before after the next one. Like there's like entailment problem that becomes, this entails the other one. Yeah, contextual, basically, understand this.
Like the example which we just saw, where we replaced pizza with the vent, and there was one masking also. So therefore, for this, we do one at a time, right? We just mask we do mask and replace all together.
Random. If you think about it, it was like 80%, 10%, 10%, cannot be one at a time, right? But it's lots of masking. We will see an example of it if we go down. Yes.
So for the segment embedding, right? So multiple tokens can be part of one sentence.
Yeah.
So for the
as you can see here, A, B, B, B.
So they all have the same
value. You just want to say that these belong to the same sentence, these belongs to the next sentence. All right. So this becomes an example of like you can train BERT for. So word embedding goes to transformer, and you make prediction depending on what you are trying to predict. Now BERT has different versions. BERT base had 12 layers, 760 dimension, 110 million. BERT large has 24 layers, 340 million parameters. And as part of the pre-training, it was pre-trained on 64 TPU chips for over 4 days. And you can fine-tune it over 1 GPU now. So you see the benefit of fine-tuning versus pre-training. So pre-training, not everyone can do that, but the idea is that pre-train once, fine-tune so many times, because everyone with 1 GPU basically you can do the pre-training, the fine-tuning.
That mask, we have 2 outputs of the model?
We will see. Just let me bring one better example. Let me see if I have. Yeah, look at the example here on BERT. It's a bit small, but as you can see here, mask, 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 mask. Right? That's like a span, right? So you don't mask only one token, you mask a span of tokens, basically. Depending on the types of the BERT that you see, this will change. Okay.
So the error can propagate.
Yeah, it's just a forward backward propagation.
No, the error also, so the first prediction, if it's incorrect, it's masked, second naturally becomes wrong.
Oh, I see what you were saying. Not, I mean, they have some basically impact probably on each other based on the attention. But it also depends on, at first, probably that impact is much higher, but as you go through iteration, that impact becomes less. So. All right, so fine tuning for the BERT concept, you can fine tune BERT for text classification, for you use that CLS token that I told you, the first token that was added at the beginning of the sentence. You can use word level classification, like you ignore the CLS and use the actual word representation. You can do text span prediction, and text span prediction is when you predict this sentence, text comes after the other one, or you drop multiple words as a span. A span means the sequence of words. You drop those and you see that the model predict the whole, basically a span. So you can, your span could be one word, could be two words, could be longer, basically a span of missing words. And depending on what's the downstream task, as you will see, the part that the model does is the same. This is the same pre-training. The fine-tuning part is changing. What you're adding here to the model to produce as an output. So that's the last part that is basically changing. The first two parts, like embedding and transformers, are the same. So these are the popular tasks you can use basically BERT over, like lots of linguistic basically tasks. Now, so now there are lots of research going on in basically in the field that, okay, how could we optimize this fine tuning? Right? Still, fine tuning is not cheap. You know, just how could we optimize it better? Because sometimes you might want to fine tune not only the last layer, maybe you want to fine tune the entire model, part of the models, stuff like that. So there are different fine tuning, basically a schema we're going to go over. We start with something called efficient fine tuning. And efficient fine tuning, basically the idea here is that you keep almost everything frozen except for certain layers. You know, there are certain layers of the model that you keep basically, you let those to train in a backward propagation. Not everything. Maybe some from the start because you want to have a learning, some from the end because you want to have a conclusion, and some from some center layers, basically maybe based on some percentage or something, is also not random, you know. But that becomes like an efficient fine tuning. So basically, you still do the fine tuning, but over percentage of the weights, basically. Yes.
So can fine tuning be used to expand the knowledge of the GPT? Because so there's a big problem these days that GPTs aren't up to date with 2025 knowledge, right? So would it be wise to fine tune it or do new knowledge or retrain the base model with more knowledge?
I don't think I'm the correct person to answer that question. I really don't even know what's going on in those GPT models. There's like nobody knows. So you don't know how they do the training, how they do the fine tuning and stuff like that. But I don't think that you retrain a new model. I don't think you start from scratch. You have all the good knowledge. You do a transfer learning, knowledge distillation, stuff like that. So it's kind of pretty wasteful if you just want to do a retraining. But again, I really don't know what they do as part of the strategy for.
They just add a hidden layer and then say.
I know. Okay, so the next one is called prefix tuning. So prefix tuning, the idea here is that you, similar to that CLS token, so now you're adding additional learnable parameters, additional tokens to the beginning of your sentences, and you learn for those tokens. And the idea of this prefix tuning was like everything else is fixed. I just keep adding certain basically fixed tokens to the beginning of my sentences. And later I want to use those tokens for the downstream tasks that I have. similar to the CLS again. So that becomes the prefix tuning. You keep everything fixed again, just you add a couple of words at the beginning of the sentence that you have. Now, the next one is LoRa, and this is one of the ones that become pretty popular and showed itself to be pretty useful. Or if you want to do fine tuning the entire model in a really optimized way, basically, LoRa. And so LoRa basically, it's a low rank, basically adaptation, and so do you know what's low rank matrix? Who knows what's a full rank matrix?
The minimum number of rows equal to
When the
Yes,
number,
the rank is equal to minimum of m comma n.
So full rank matrix is that when the number of, so rank of the matrix is defined by basically maximum number of linearly independent rows and columns, right? If you look at matrix, if your rows are all independent, columns are all independent, that's a full rank matrix. Right? So overall, a full rank matrix basically becomes when the rank is equal minimum of n and d, right? That's full rank. And low rank matrix is when that's not the case, basically. So we will say that if matrix A, I'll say if n by d, it's low rank, that means if you do something like SVD, for example, singular value decomposition on A, and you get U sigma V transpose. So if this is n by d here, maybe you get, for example, n by r, here you get r by r, and you get r by d. Okay, where r is the low rank degree, basically. Okay, so and an example of the low rank basically decomposition also is like a PCA. Like PCA is basically does similar idea, like goes to a low rank representation. Now, this basically the way that it's this is like a transform version of it. Actually, if you look at it in a general way, if this is n by n, this could be n by d, and this could be, for example, d by d. But here, across the singular values, so rank of a matrix also basically becomes the number of non-zero singular values, right? Well, you will find in a low rank matrix when you do singular value decomposition, if you have d dimension, p of them have a singular value of almost zero. So the rank becomes d minus p. That becomes a low rank matrix, right? Now, the idea here is that if we, let's say you have this model, and this model has lots of W's. When I say here W as a transformer, if you think about it, you have WQ, you have WV, you have WK, and you have series of those based on the multi-attention, multi-layers, and all other layers, all other weights that is in this matrix, in this model. Now, let's say you want to fine-tune this model, but you don't want to go through that cost. The idea here is in the LoRa is that could we, so if you want to update the weight in a gradient descent, what do? Weight, like a WQ basically becomes previous WQ minus some delta WQ, correct? You find some gradient basically. Finding that gradient is costly. Okay. So now the idea here is that could we approximate this gradient? Let's drop that, just this. Could we approximate this gradient using a low rank matrix approximation? That's the idea. Instead of calculating it, approximating it. Now, how do we approximate that? So we will basically say that delta W comes from, so delta, what's the dimension of delta W? Let's say your matrix is d by d, WQ is d by d. So delta WQ is also d by d, correct? All you need to do is that find two matrices, A times B, that the multiplication becomes d by d. So one of them, let's say, is d by 2, the other one is 2 by d. So you only learn d by 2 for one and 2 by d by the other one. Multiplication of that gives you d by d updates. Does that make sense? So the idea will be that I want to, instead of binding this, I'm going to use this as WQ minus A times B. That's my update. And you always keep this, basically during the forward, during your training, you actually don't update this. You keep track, you only focus on making this better. So you do a forward pass with WQ. With this WQ, basically, you get this new value, okay? You do a forward pass with it, and you want to do backward. When you do backward, you don't do gradient on this. You only do gradient on this. That's always fixed. In every iteration, WQ remains fixed. The only thing you update is A and B. So think about this. So I have at time t equals 0. I have WQ. And I basically say that WQ, I add some random AB to it. Okay? Now I get this WQ prime. Okay? I just did some updates on it. Then I do a forward pass. Forward pass. Then I get cost function. Then I do backward, right? When I do backward, W is fixed. I update W using AB. So I see how much AB should be penalized. So I update AB to account for the cost, for the errors that I have, not the W. The AB is responsible for that, right? So you do backward propagation, you update A and you update B separate, because there are two separate matrices. You find gradient with respect to A, gradient with respect to B, and A becomes A at time t equal 1 becomes A at time t equals 0 minus gradient of J with respect to A at time 0. At time 1 minus gradient of J with respect to B at time 0. So now I found the gradient of A and B, update A and B. Now I basically go to the next iteration. I still use the same W. I don't update the W. Now I haven't updated A and B. I just focus on A and B. Because if you update W, you went through the whole calculation and you also have A and B on top of it. So you keep always your weights fixed. You only update this part, this smaller matrices, and gradient only on that smaller matrix. Your goal is that by keep iterating to find this A and B somehow, that if you use this A and B, you get perfect downstream task, classification, regression, whatever you're doing. Does that make sense? That's called LoRa, basically the low rank matrix adaptation, because instead of doing a full finding the full delta W, you break delta W into two low rank matrices. The dimension is not, is basically R. You decide what makes more sense, like for your data. But I only need to learn these two smaller matrices, and it's much faster. You can do basically LoRa in much faster on one GPU, basically, in compare and do a fine tuning, basically. Okay, so if you do for your project, you try to do fine tuning or something, LoRa is one of the techniques that do. Actually, there's another version of LoRa. It's called QLoRa. Yes, so QLoRa is the quantized LoRa. Right? The idea behind quantized, you know, the quantization in model training. So you train a model, and you're like, well, neural networks basically they give you weights and when you're looking at your weights, depending on the library that you're using, but normally the weights have decimals, right? So they have this decimal, probably float 32 or float 64, right? So it's like you will see a number that is like kind of like a long numbers. The reason for those long decimals is that the model tunes a lot to adjust. A small change might have a drastic output if your model has overfitted. But the idea here is that if you have a good model, it shouldn't matter much if I drop the last 2 decimals, or if I drop the last 3 decimals. You quantize it, bucketizing it. You go from float toward integer. So instead of, for example, having float 32, you might go even int 8, int 16, int 32. Right? So I personally, the previous company that I was working that we were doing a mobile deployment. So we developed models, and float models, they are not really good for mobile computation. You want it to be quantized. So we normally go from all the way from float 32 to either int 8 or int 16. And normally you lose some accuracy, but we were basically, there are some techniques to avoid that, to do like a quantized aware and stuff like that. And we almost, sometimes you get even better results, like a higher, because you get rid of lots of noise that the model might carry because of those decimals. So here, the idea of QLARA is that you do the same thing, but during the forward pass, you quantize these weights. So these weights, instead of being a large float, you make them much smaller integer, then you do the forward pass. You still only learn A and B, but during the forward pass, you use a quantized weight, so the model basically learns that, okay, the weight should be smaller. So that becomes QLAR, like that's LARA, that's QLAR. Just the only difference here is that adding this quantized layer before W during the forward pass. Does that make sense? And again, in either scenario, you do not update your weights. It's just, you only update A and B, basically. Okay, so.
We need delta W to have A and B. We wanted A and B to.
This is the same thing. Delta W equal A times B.
But we wanted to use A and B to not use delta W.
Yeah, so but that's the same thing, right? So delta W is, let's say, D by D.
No. Are we calculating delta W, and from delta W we calculate A and B?
You find A and B, A times B becomes delta W.
Oh, it's just some random matrices, and then
You learn that random matrices. The two smaller matrices that if you multiply them together produce a larger matrix. So instead of learning the larger matrix, you learn the smaller matrices and multiply them together to produce the larger one. And yes, that's what they did. So that's the idea of LoRa, QLoRa, and this is the whole math behind it. Number of parameters, this becomes D times R plus D times R, 2D times R. That's the number of parameters basically you update for any weights. You have a series of those. Now,
So
yes.
in this, we have like kind of like an assumption, right? That our base WQ that we are starting from is a like
Pre-trained model, good model, base model, yeah. All right, so see, I think we can stop here on end of the LoRa and QLoRa, and then we can start continuing the next class.